and good afternoon, everybody. I hope you are not going to sleep too much over the next 40 minutes. As many of the speakers you have already listened to over the last 2 days, I'm from Innsbruck, and I'm working with Rudy in an experiment investigating lithium-6 potassium-40 Fermi-Fermi mixture. The plan of the talk is to give you first some very naive motivation and I hope useful experimental details which, let's say, make our system a bit different with respect to usual Fermi mixtures of same atomic species in different spin states. And then I will go to present recent results we obtained when studying potassium-40 heavy impurities embedded into a lithium-6 Fermi sea, which you can find into this paper. And then I will spend few minutes describing ongoing experiments investigating the repulsive branch of a heteronuclear Feshbach resonance when the potassium atom number is not so little. All right, so general idea is take ultracold Fermi gases. They are, in a sense, systems with many interesting analogies with other systems with unprecedented control over temperature, geometry, dimensionality, interaction strength, and many other things that allow you to have a set of precious knobs to investigate such systems. And if you go to Fermi-Fermi mixtures, namely mixtures of two distinct atomic species, fermionic species, you have two additional knobs, at least that come into my mind. One is clearly the mass imbalance, that is interesting in view of few body physics, as we have already heard, for example, by Pascal. And also qualitative and quantitative changes can arise at the many-body level into the phase diagram of such Fermi mixtures. The other one is the fact that since we deal in this case with two distinct atomic species with, let's say, not only different masses but completely eventually different properties from the optical point of view, you can think of implementing species selective potentials which allow you eventually to make individual trap or individual moving systems keeping the second species unaffected. And this kind of ability culminates in a series of interesting prospects for what concerns, for example, mixed dimensions that Yuzuke has worked quite extensively on over the last years. All right. So if you take just the first column of alkali atoms, it's quite obvious that a prime candidate for realizing such a Fermi-Fermi mixture is lithium-6 potassium-40. Each of the two atomic species have been investigated extensively over the last decade with fantastic results. And I just stressed that combining these two atomic species allow you eventually quite easily to reach other Bose-Bose and Bose-Fermi mixtures with quite not so much effort. All right, so our starting point coming from an all-optical approach for preparing the system can be visualized as it follows. We deal with a quite huge cloud of lithium-6 atoms in a single spin state, which is quite a degenerate Fermi gas, and embedded into this huge cloud of lithium, we prepare a smaller, at least, cloud of potassium atoms whose number ranges between 10,000 and 60,000 with, depending what do you want to investigate. All right, these two clouds are trapped in a crossed optical dipole trap at 1064 nanometers, and you can clearly see the effect, let's say, of the two things I was mentioning before, mass imbalance and, let's say, different optical properties of the two atomic species. It turns out that such a potential is more or less twice as deep for potassium as than for lithium, 6 atoms. So therefore, despite the fact that we deal with a strong imbalance in the number of the two atoms, we can easily range just varying between 10,000 and 60,000, and vice versa between 400,000 and 100,000, from a situation, let's say, which I would call BEC, BCS, meaning that you deal with a balanced density at the center of the trap, towards a situation in which instead the potassium 40 is really not only quite small in number, but also quite low in density compared to the lithium. For the next of the talk, you can consider that our system is composed by about 2 times 10 to the 4 potassium atoms, which form a moderately degenerate Fermi gas. You can, at 0 order, consider that it's almost a thermal gas of potassium atoms embedded into about 350,000 lithium-6 atoms at a Fermi temperature that is at the temperature which is about 0.14 of the Fermi temperature. So at 0 order, if you want to, let's say, oversimplify what we deal with, you can think that we have a small thermal sample of potassium atoms embedded into a 0 temperature Fermi C of lithium. Yeah? And indeed, this is basically characterized by a relevant energy scale, which is the averaged lithium Fermi energy, averaged meaning averaged over the density distribution of the potassium cloud, which is about 37 kilohertz. Correspondingly, the Fermi wave vector is about 2,800 A naught to the minus 1. Yeah? All right, so you want to do, indeed, with such a system, some many-body physics, so therefore you need a ability of control the interactions between these two species. And here it comes, let's say, a not so nice part of the story of such a mixture. We actually exploit a Feshbach resonance between the absolute internal state of absolute ground state of the lithium-6 atom and the third to lowest Zeeman sublevel of potassium-3. It is a Feshbach resonance which is located around 154.720 Gauss, and as you can see here, this is about 900 milligauss wide, which is completely a different regime and scenario with respect to, let's say, potassium 40 spin mixtures, or even more dramatic lithium-6 spin mixtures, where the width of these resonances can range between 10 and 300 Gauss. Yeah? If you plug in the numbers here with such a Fermi wave vector, you will discover that the strongly interacting regime can be achieved only within a quite small region near to the resonance center, let's say plus or minus 20 milligauss. Yeah? The final thing that I want to stress is that since this resonance, and trust me, this resonance is probably the most favorable resonance we can deal with, it occurs in an excited state of such a mixture, which means that unfortunately inelastic two-body decay is allowed. Yeah? So therefore, for example, lithium-1 potassium-3 can inelastically collide and go into lithium-1 potassium-2 or lithium-1 potassium-1 state, releasing a lot of energy. And it turns out that such an inelastic process is resonantly enhanced at resonance, and at resonance with the typical densities and temperatures we deal with, you cannot hope to have a lifetime due to this two-body inelastic decay, which is longer than 20 milliseconds, I would say. The final thing I want to stress is narrow Feldspar resonance means not only that it's narrow the width, yeah, but it's narrow meaning also that the effective range associated to this resonance is going to be huge. This is visualized if you look at this parameter, which is usually defined as -1/2 the effective range is equal to this R star parameter, and it turns out you plug in this the numbers and it turns out that this R star for our system is on the order of the inverse Fermi wave vector. Yeah, so therefore you can obviously expect that tuning the interaction in such a system is not an easy task. From the experimental point of view, you have to deal with sort of a system whose lifetime is not going to be extremely long, and you need obviously a nice magnetic field stability if you want to put a significant amount of points into the strongly interacting regime when you do whatever experiment you want to do. And also the presence of this large effective range might be quite challenging from the theory point of view. Yeah. All right, that's only, let's say it starts not very optimistic, the thing, but now I want to show you that probably you can still do things which are interesting in such a system. So if you look at the numbers we can typically achieve in the experiment, one kind of natural thing to investigate in such a system is, let's say, the behavior of potassium impurities when resonantly interacting with lithium Fermi C. And in this case, we are in the so-called Polaron scenario, in which, let's say, such a many-body system is efficiently describable in terms of fictitious particles, namely quasi-particles called Fermi polarons, that are, let's say, fictitious objects indeed with which behave namely as free particles whose energy and mass become renormalized, which acquire eventually a finite lifetime and are characterized by other properties. I want just to stress one of them is the so-called quasi-particle residue that tells you essentially within this polaron how much is left of the real particle. All right, so if you look at the energy landscape of such a many-body system in the limit of 0 temperature and a single potassium impurity, then you can have a look at the spectral function of the system. Here is as a function of the interaction strength. Here is the energy renormalized to the Fermi energy of lithium. And yeah, I don't want to enter much into the detail because I think Pietro will discuss more in depth these kind of things in the next talk. But this is something that is evaluated for our system with a Fermi energy that is the Fermi energy we deal with and with a KF R star parameter which is around 0.95. Since it is a narrow resonance, you can expect that qualitatively the scenario will stay the same, but quantitatively it will change as you move, let's say, your Fermi energy and this KF R star parameter. Yeah. All right. This spectral function is characterized by an attractive polaron branch, which represents the ground state coming from the BCS side of the resonance until a certain interaction strength, after which the system prefers to do the following. The potassium atoms prefers energetically to form a molecule with just picking up a lithium atom from the Fermi C. Associated to the presence of this molecule state, there is a continuum indeed of states. And this can be understood by the fact that, let's say, the potassium atom can bind into a molecule just picking up any lithium atom from the Fermi C, ranging from the bottom of the Fermi C up to the Fermi energy. And that's the reason why, at least far in the BEC limit, such a continuum of states extends from the molecule binding energy up to the molecule binding energy plus EF. Interestingly, there is also another polaronic branch which increases its energy as the resonance is approached now from the BEC side, and it is a so-called repulsive polaron, at least according to the first definition I think was given, was coined by Stefano and Sebastiano Pilati in a PRL of a couple of years ago. All right, so how do we probe such a system? We probe this system by means of radio frequency spectroscopy, and the idea is to exploit so-called reverse spectroscopy, as Rudy likes to call it. That is, namely, you prepare your system in a non-resonant state in proximity of the lithium-1 potassium-3 Feshbach resonance, and then you apply a radio frequency pulse which eventually, which eventually will transfer the potassium impurity from a non-resonant state into a final state which is strongly interacting with the medium. And that's not the standard way, despite the fact that such a scheme was exploited, I think, in the early days of the investigation of ultra-cold foamy gases, for example, by the Begin group. All right, so basically, for just giving you an idea about what is the experimental procedure we exploited, we just brought the system to a final field close to this Feshbach resonance in a non-resonant state. We put initially the lithium in not the absolute ground state, so therefore there will not be interactions also when potassium is transferred into the tree state, and we simply take a field calibration, yeah? And such a field calibration allows us, for example, just to know where we are with the magnetic field, and in addition, let's say the width of such a calibration spectrum allows us to know that our field stability is better than 2 milligauss, so therefore we have some chances of putting a decent amount of points into the strongly interacting regime. Right, then we repeat exactly the same scan, but now switching on the interaction, so therefore lithium is now in the resonance state, and we take a spectrum. Yeah, and for example, here we are on the BEC side at something like KFA on the order of 0.5, and let's say this is just the reference, the calibration, and you can see that we can observe two features in this case. For example, a positive shifted feature which corresponds to the repulsive polaron we were discussing before, and a broad feature in this case shifted towards lower energies that correspond in this case to the presence of this molecule hole continuum. We repeat this for many fields, scan over quite a decent amount of points, then you put all the spectra together into a false color plot, and then you end up with such a scenario, which is quite nice. Indeed, let's say we can clearly see both polaronic branches when doing such a spectroscopy. We find a good agreement with the theory calculation carried out by Pietro and Georg Brun. For what concerns the attractive polaron, we see that such an attractive polaron peak almost disappears at the edge of the strongly interacting regime, which is, let's say, kind of expected, considering the fact that we expect that this attractive polaron in the vicinity of such interaction strength will merge into the molecule hole continuum. And what is quite nice, that the repulsive branch instead is quite clearly visible up to a very strong repulsion, and this is quite an interesting thing. In order to unveil the presence of this molecule hole continuum, we had to increase significantly the radio frequency power of when doing the spectroscopy, due to the fact that molecules have quite a reduced Frank-Condon overlap with the state you start with. And you can see that, let's say, the result matches fairly well the theoretical calculation. And I think that you have already kind of seen such a picture that was put by Rudy on the booklet. It's also interesting, I don't want to enter too much into the detail, but it's very important the understanding of the spectral shape of such a molecule whole continuum far away from resonance. As Martin Zwirlein was saying yesterday, this, let's say, can be kind of easily understood in terms of simple line shape models, and this is very important for us because based on essentially the analysis of the spectral response far on the BEC side, we were able to pinpoint the resonance center with very, very high accuracy on the order of, let's say, 2 milligauss. All right, so let's say clearly such a repulsive polaron, which seems to be kind of nicely visible in our system and that had never been found in, let's say, on the nuclear system, as far as I know. It's quite interesting, and obviously such a state is clearly a metastable state, yeah, because the closer you go to resonance, the easier will be, or the easier will be for this guy eventually to decay onto lower line states, which will be pretty close in energy, namely either the attractive polaron or the molecular excitation. So let's say based on the knowledge we had from the previous characterization of the spectral response for each magnetic field, we knew exactly where the polaron is peaked compared to the molecular excitations. And in order to investigate the lifetime of such repulsive polaron, what we did was to apply a 3-pulse scheme that consists of the following thing. A first pulse selectively transfer the non-resonant potassium into the repulsive polaron state, simply setting the radio frequency at this value. A second pulse cleaned simply the non-resonant remnant atoms of potassium. Then we waited for some variable time, during which eventually the potassium polarons could decay. And finally, a third pulse, exactly analogous to the first one, selectively transferred back this remnant repulsive polaron into the non-interacting state. And there we can measure selectively the population which survived of the repulsive polaron as a function of the holding time. We did this for several fields. Here you can see some sample curves as a function of the interaction strength, and we end up with such a graph. These are the experimental points. Here are 2 theory curves which take into account either a 3-body process in which the repulsive polaron undergoes a 3-body recombination process that brings the polaron into, converts the polaron into a molecule, and this other line is taking into account the possibility of having this repulsive polaron that first decays into an attractive polaron and then further decays via a 3-body process into the molecule continuum. And let's say what I want to stress here is that such a lifetime, which is renormalized to the Fermi energy, is extremely long. It means if you take in mind the previous characterization I was showing you about the energy of such a repulsive polaron, at this point here, the energy of this quasi-particle is on the order of 0.3 times EF. And you can see that the lifetime associated to this quasi-particle is on the order of 10 to the minus 2 EF, which means that also very, very close to resonance. The lifetime of this quasi-particle is extremely longer than, let's say, the decay rate is extremely small compared to the energy of such a state, which means that our repulsive polaron is a pretty long-lived quasi-particle, also very, very close to resonance. Interestingly, it turns out that, at least that's Pietro and Georg calculations, it turns out that there is a very strong benefit for this related to the presence of this R star parameter being on the order of the inverse Fermi wave vector. And this is very interesting in the sense that these allow us to have almost the same amount of energy that you could achieve in a hypothetical system with a broad resonance, but with a gain in lifetime by almost a factor of 10, which is very, very important. All right, as I was telling you while briefly discussing what a polaron is, one important quantity that characterizes the quasi-particle is this Z, this residue. Yeah? And we had an idea about how to get information about this quasi-particle residue, and this is based on exploiting the possibility of making Rabi oscillations with our RF field. So the idea is the following: take a non-interacting system, yeah, just potassium atom, and then you set the radio frequency at the resonance frequency between 0 and 1 state, and then you will see nice Rabi oscillations characterized by a Rabi frequency which is proportional to the expectation value of the RF operator between these two states. Now you switch on the interaction and you replace the one state with the polaron state. Yeah? In this case, omega will be proportional to the expectation value of the polaron, of the RF operator between the polaron and the initial non-resonant system, which is made by a 0 potassium atom and an unperturbed Fermi C of lithium. And it turns out that this directly relates to the unperturbed Rabi frequency, which you can measure up here, and the square root of Z allows you to determine right away the quasi-particle residue if you just measure the Rabi frequency at the repulsive polaron or attractive polaron peaks. Again, we did this for several interaction strengths on both sides of the resonance, on both attractive and repulsive branches. And it turned out that the two, so basically two major effects are visible into these curves. One effect is that the Rabi oscillations are visible, but they get more and more damped the larger is the interaction strength, the closer we go to resonance. And the other thing, which is, let's say, what we wanted to see indeed, is the effect that exactly this omega over omega 0 fits remarkably well the square root of Z behavior for the attractive and the repulsive polaron as calculated by Pietro. I want to just point the attention to the fact that the damping of such Rabi oscillations is almost a factor of 10 larger than the decay, for example, that we have measured for the population of the repulsive branch, which means that it's interesting that this damping rate is mostly due to decoherence rather than to decay of population. And this is also an interesting thing that is kind of under investigation right now. Good, so that's the end of the first part of my talk. I have shown you a quite extensive study of potassium-40 impurities in the lithium Fermi C, and by means of radio frequency spectroscopy we could have information about attractive and repulsive polarons, and we could measure their quasi-particle residue by exploiting a novel measurement scheme. And yeah, there are many nice things that one can find out in this paper, but let's say what we are interested and mostly excited for is the presence of this long-lived repulsive polaron. And that's, let's say, bringing me to the final part of my talk, and which concerns the investigation of the repulsive branch in such a system. So, let's say, why repulsive polarons were introduced? Repulsive polarons were introduced in the context of studying the stability of a fully ferromagnetic phase by the work by Stefano Giorgini and Sebastiano Pilati. Essentially, the energy of repulsive polaron tells you if, let's say, a repulsive gas which is phase separated will stay phase separated at a certain critical interaction strength. Why? Because if you just consider the possibility of taking, for example, a blue particle and put into the Fermi sea of red particles, you will find out that this particle will create a repulsive polaron. If the energy of such a repulsive polaron is too high, the system will not mix. That's the idea. However, this is an interesting thing, but it's very, very challenging at the Feshbach resonance, and recent work by Wolfgang Ketterer's group on nuclear lithium-6 mixtures pointed out that it's very challenging because it's very unstable, unfortunately. Essentially, in the calculations carried out by Stefano and co-workers, let's say the presence of a Feshbach molecule below the scattering threshold was by definition taken out, but this is something that in reality, unfortunately, you cannot do. So therefore, you never know whether such a mixed system, as you crank up the repulsive interaction, will have time to reach such a state, or rather will form, let's say, a gas of molecules. Okay, so our repulsive polaron is long-lived, and we were saying, okay, a natural thing to look is whether we can do something in this context with such a system. Considering the fact that we have such a mass imbalance and different trapping potential, in our case, if repulsive interaction is sufficiently strong, then, let's say, the formation of domains due to repulsive interaction will turn out to be kind of pretty simple, in the sense that the system will tend to phase separate, with potassium cloud being squeezed in the center of the trap and lithium being pushed out. If this happens, let's say a series of observable will unveil this thing. Especially if this happens, atoms losses will stop, because they will basically not touch anymore except at the interface. Potassium size cloud squeeze, and correspondingly the kinetic energy of this potassium cloud will increase. At the other hand, let's say the lithium will have a hole basically in the center, and accompanied by this, the radio frequency shift, which you can measure using the techniques I was explaining you before, will almost go to zero, simply because potassium will not be merged anymore with the lithium. So to investigate such a scenario, what we do most of the time is the following thing. We prepare an interacting system, this time at the repulsive branch of the Feshbach resonance, quite far from resonance, and then we just make a magnetic field ramp up to a certain field. This magnetic field ramp can be either fast or slow. Yeah? Let the system evolve, eventually associating many, many molecules. And afterwards, we monitor potassium, lithium atoms, and molecules. And to do so, we just ramp back quite fast to a place where essentially the molecule binding energy is on the order of 100 kilohertz. The system is again weakly interacting, and by applying radio frequency pi pulses, we can selectively transfer into other states the atomic populations and leaving the molecule into the final state, and then selectively image all of them. Okay, so the first thing we did was to look at atom losses after a fast ramp to a final field, yeah? And these are again typical decay curves we observe, and this unfortunately is the lifetime we measure, which matches fairly well within, yeah, let's say the error bars we can have in the experiment, the lifetime which we measured for the repulsive polaron, which is not very, very nice. On the other hand, just look at these two features. One, let's say, is on the order of KFA equal 1. The other one is quite close to resonance. And you see a funny thing. This decay curve tends, let's say, to go to 0. So basically, it's well fitted by a single exponential decay. This curve, let's say, is characterized by a very fast decay, but then the system seems to not lose atoms anymore. And let's say if I just plot the remnant atoms out of a single exponential fit as a function of the interaction strength, or alternatively, I just evaluate the lifetime of the system just taking the data from 0.5 millisecond the whole time on, I can clearly see that there is something quite funny happening within a region of magnetic field where the KFA for the non-perturbed Fermi sea is on the order of 2. It means essentially that from here on, after a very fast dynamics, we have an almost static behavior of the system for what concerns the losses. And I want just to point out that a similar trend was observed recently in lithium-6 mixtures in Wolfgang group. Okay, it's nice also that this kind of thing is not something that you simply say, okay, I have just destroyed completely my system, and then it's simply heated up like crazy, and this kind of static behavior is simply due to the fact that I have heated up and depleted completely my system. Indeed, if you just go close to resonance, you wait that this fast dynamics is gone, and then you fit the data staying at the final field, you would get such an offset. Yeah. Now, if you ramp after this fast dynamic has taken place down again in interaction strength, so you basically lower the repulsive interaction, you see that the atom number after a certain time over which nothing really happened, it starts decaying again. And if you fit this line here, you will find out again a very similar decay rate or lifetime as measured if you were just measuring the whole lifetime staying at this final field. So to some extent, it's something like this kind of static behavior observed very close to resonance. It's something that clearly is heavily affected by the loss of atoms and conversion into molecules, but it's to some degree sort of still reversible. Yeah. It's also interesting to see what it happens if you look at the kinetic energy of the potassium distribution as a function of the repulsive interaction. You can see that going closer and closer to resonance, where more or less this decay after fast dynamics stops, the kinetic energy shows a sort of saturation. And what is interesting also, in my opinion, is that if you look at the in situ cloud of the potassium component as a function of the interaction strength, let's say this increase of kinetic energy is accompanied not by an increase of size which would suggest a heating effect, but rather it's squeezed towards the resonance. Yeah? And this is quite interesting. And finally, let's say, if you take an in situ picture of the lithium component, you can clearly see that when this phase is reached, let's say, considering the fact that, however, you have almost 10 times more the lithium atoms than potassium atoms, you can clearly see that here there is a quite visible hole in the lithium density distribution. Okay, I think I am done. Yes. So in conclusion, let's say there is many other stuff ongoing concerning this repulsive branch study. Especially we are doing radiofrequency spectroscopy, and we are looking at interesting features occurring as a function especially of temperature. What it happens as a function of temperature is something quite nice but not well understood yet. Our data, in my opinion, suggest kind of strongly the presence of a region very close to essence where separation between potassium and lithium components occur, despite the fact that it's absolutely not definitively clear the role played by the molecule formation, which we have for sure in the system. And yeah, I didn't discuss in this talk, yeah, and I think that's clearly enough. Other things that are ongoing in Innsbruck experiment, especially what it happens at the attractive branch for what concerns the BEC-BCS crossover. Many things interesting possibly will occur at P-wave resonances, which are present in our system, but that's a different story. And with this, let me conclude. I thank you for your attention, and especially I acknowledge these three guys that carried out many of the experimental work. Thanks a lot.
One or two questions.
Yeah, I'm sorry.
Yeah, that's on. Sir.
It's really very interesting and exciting what you are doing with this mixture. Would it be possible to measure the momentum distribution function for the potassium atoms? I mean, by switching on the trapping potential and the magnetic field. Would it be possible? Because in the molecular regime, because if it would be possible,
yeah.
You could measure essentially what I was telling yesterday for the bosons. You should see an empty region in momentum space due to the Pauli repulsion of the lithium atoms.
Let's say, in principle, yes, in the sense that the momentum distribution is kind of measured here. Let's say this measurement comes out simply by fitting to a Gaussian distribution, the whole cloud. What I should do is looking at the image and try to get information about...
I mean, time of flight measurement.
Yes. Let's say I should look at the image and see if there is a hole in the center. That's what you mean?
No.
No. Then we have to discuss after. Sorry.
There's a pressing question. Quick.
Yeah, I have a question related to...
Yeah, I told you not to ask for questions, but okay, that's fine.
So probably it's not so nasty. So you showed here essentially that the decay rate into molecules is not so fast, or at least you when you approach the resonance, you have less production of molecules, and the kinetic energy goes to a maximum, which, if I remember correctly, was more or less the same evidence that was obtained by Wolfgang Ketterle in the first experiment.
Yes.
Then they, by looking again at the data, they concluded that, okay, so this phase separation or ferromagnetic state was not present. So here you think there is something different?
No, I think, let's say that definitively it's a much more complicated system with respect to the idealized one where no molecule formation is expected, yeah, And clearly we have a strong molecule formation as we approach the resonance. I mean, indeed the lifetime, if you look at the whole dynamics, is fitting fairly well the repulsive polar on lifetime, which means it's something that continuously goes down as you approach the resonance. Yeah, that's exactly Wolfgang Ketterle experiment, I think. The thing is, let's say, what I'm not sure about is that in both cases, let's say, after this fast molecule formation, you cannot have something more ongoing. And let's say, in our system, looking for domain formation is something very easy in the sense that domain formation for us means a macroscopic domain at the center, being potassium, and a macroscopic domain being lithium at the edge. In case of Wolfgang Ketterle experiment, in a sense it's much more interesting, if you want, in the sense that you have no symmetry breaking because you have exactly the same trap, exactly the same atom number, so therefore, let's say, this domain formation is not obvious how it has to occur, and eventually it occurs on a very, very small length scale, which is quite tough to be observed. Let's say, I'm